So, good morning all of you. Yesterday we looked at the Boltzmann distribution function, how we derived the Boltzmann distribution function from simple probability assumptions, and the most important thing about this distribution function is that it gives you what is the filling or the number of particles that can occupy the energy levels, what is the order in which they occupy, So, this is the most important consequence of the distribution function, and also according to the kind of system that you are dealing with, you can talk about what we call as canonical or grand canonical. These are the two most common ensembles, and we fit the system with phonons, molecules and photons to the canonical ensemble, and the electrons are usually assigned to the grand canonical ensemble. So, accordingly we can write down the probability distribution function for the canonical ensemble, which looks like this, and for the grand canonical ensemble like this. So, having now identified the corresponding distribution functions for the corresponding energy carriers, we will now apply this to derive the the distribution function for each and every energy carrier. Okay. So, therefore, this is not just sufficient if you are looking at only the the probability of distribution of these particular energy carriers. From this we have to first calculate the denominator, which is the partition function. Okay. This is the summation term. So, this is still not complete, and we have to also apply the corresponding energy levels. Okay. So, this is a generic form here. So, depending on you are dealing with molecules or phonons or photons, the appropriate values of energies have to be substituted. So, we have to evaluate the partition function in the denominator and then come to the distribution function. Okay. So, today we will start with applying this for first molecules. So, let us first start with molecules, which are more familiar. We do not even have to do any quantum mechanics to understand the energy levels of these molecules. So, these are basically continuous energy levels, right. You do not have to apply any quantum mechanic principles for determining the energy levels here. And if you are talking about a monoatomic atom, typically the one that we will now consider, monoatomic atom. So, this is just one atom like this, and it can have translational motion in all the three perpendicular directions. So, you can have Vx, Vy, Vz. So, therefore, the corresponding energy that possessed by this particular atom, so can be just half m Vx square Vy square plus Vz square. So, it has 3 degrees of freedom for kinetic energy, translational kinetic energy, right. So, there are no vibrational modes, there are no rotational modes. So, purely translational kinetic energy. So, therefore, you see this Vx, Vy, Vz are continuous energy levels. So, you can actually span from minus infinity to infinity depending on the direction that they are moving across. So, now we will substitute into the definition of partition function. Okay. Now, we know which distribution to pick. So, we look at molecules, therefore, they belong to the canonical ensemble. So, we can therefore calculate the partition function accordingly. So, your z will now be summation e power minus ei by kb t. Now, for a continuous function, so we will use the integral instead of the discrete summation here, right. So, the summation is good as long as you have discrete energy levels, but if you apply this for molecules where you have continuous energy levels, so this can be replaced as a summation. And now how many integrals you have? You have 3 integrals, one in x, one in y, one in z. So, you have minus infinity to infinity, and you have e power minus m by 2. I am just substituting our kinetic energies into divided by kBt, and this integral is over dvx, dvy, dvz. Okay. Is it clear? So, we are just now evaluating the partition function. In the case of molecules, these are continuous, and therefore, we replace the summation with these integrals. So, if you evaluate this, in fact, you can actually try this in a symbolic manipulation software like Mathematica, because this you cannot integrate by hand right now. Okay. So, you can perform this triple integral in a package like Mathematica, which will do numerical integration and give you the answer. So, that should come out to be m by 2 pi kb t the whole power minus 3 by 2. So, this will be the result of this particular integration, triple integral. So, this is your partition function z, and therefore, what will be your probability distribution function P E of I?
So, we will transfer that velocity Vx, Vy, Vz in the terms of x, y and z.
Yeah, you already have integrated this over minus, these are for limits for Vx, Vy, Vz.
X.
Correct, but all these are in Vx space only, there is no problem. Okay, all these are in momentum space, you do not have any issue. Okay. So, you know the limits of the integral for Vx, Vy, Vz. So, all you have to do is plug it into some symbolic manipulation package like Mathematica, and it will directly give you what is the result of this. It will do a numerical integration for this. Okay. So, once you know the partition function, now you can calculate your probability distribution. So, for this case it will be therefore e power minus ei, let us write it in terms of e by kbt. So, this is what is there in the numerator. The denominator was the partition function, now which we have evaluated. Okay. So, we will take this to the numerator, you will have m by 2 pi kbt the whole power 3 by 2. Okay. So, therefore, now what we need to actually evaluate is not just the probability, but the distribution function, the number distribution. So, how many number of molecules can occupy a particular energy level and so on. So, now once we know this probability, the way we are going to evaluate the distribution. So, this f here is actually the number distribution function for energy carriers. So, we know that P E of I is nothing but what? Actually, it is n of I by summation n of I. Okay. Now, we want to get back something like this. Okay. So, if you want to therefore get the number distribution, so we will multiply the probability by the number density. okay, that is the number of molecules in a unit volume of a system, for example. Okay, so this is a pure number. Now, what we are getting here is a density per unit volume, that is number of molecules per unit volume, it is a number density. So, this distribution signifies number density here, whereas this is just pure number count. Okay. So, therefore, for the entire volume, when you want to calculate the number density, so we will simply multiply the probability with the corresponding number density. So, this we will call this as number density here. Number density of molecules. Okay. So, the way to interpret this is, so for a particular energy level, if these were discrete energy levels, okay, so this will tell you how many molecules can occupy that particular energy level. So, that will be the number density of molecules occupying that, and finally, the distribution function will be an ensemble of this. So, that means you just sum over all these different energy levels and you allot the particular number to that particular probability and so on. So, that will give you the total number distribution function for the entire system. So, in the case of molecules, these are anyway continuous, okay, and therefore, the number itself is just a constant value. Okay. It is not going to fit into one particular discrete energy level EI, the way molecules and phonons are going to occupy. So, simply we can multiply this number of molecules or number density of molecules with the probability. So, if you do that, therefore, you will be just simply extending this as f is equal to n into m by 2 pi k b t whole power 3 by 2 e power minus, this is again m by 2 v x square plus v y square plus v z square by 2 k b t. So, this gives you the number distribution function, or this is your number distribution function for molecules. So, this distribution function is also called the Maxwell-Boltzmann distribution function. So, is that clear? So, we started with therefore, the distribution of electrons at each energy level or distribution of molecules. So, but now then we rewrote in terms of probability, and now we are coming back to the distribution function, but now this is per unit volume. So, it is a number density function. Okay. So, therefore, we multiply it by the number of molecules per unit volume of the system. So, this n is nothing but number density of molecules, or this is you can interpret as number of molecules per unit volume. Okay. So, this resulting distribution of molecules. So, this will tell you therefore, for a system with volume V with n number of molecules, so at what velocity levels, like you have Vx, particular value of Vx, Vy, Vz, what will be the distribution of molecules in this particular band of Vx, Vy, Vz. Okay, these are continuous here. So, for continuous values of Vx, Vy, Vz, it will tell you what will be the corresponding number of molecules that can occupy per unit volume of the system. Okay. So, this is a classical distribution function. Why? Because we do not have any discrete values of energy levels here, everything is continuous. So, this is usually referred to as a classical distribution, because we do not have to start with any quantum mechanics to derive this distribution function, everything is continuous starting from the energies, right. So, all we did was put it into the Boltzmann distribution function, calculate partition function, and that is it. So, there was no quantum mechanics into this. Okay. So, that is why this is called a classical distribution function. Now, if you apply this to the next energy carrier, so we will do this for electrons now. Okay. So, therefore, in the case of electrons, they obey the grand canonical ensemble. So, the probability of distribution of electrons will be e power minus E I minus mu N I by k B T by, you have the partition function z, which is nothing but summation of the numerator, correct. So, for the, as far as the electron is concerned, so where you have z is equal to summation e power minus E I minus mu N I by k B T. So, when you look at the occupation of these energy levels by electrons, so you have only two possibilities. Okay, you have a particular number. For example, if you are talking about an energy level which is empty, so that means this is equal to 0 if you are talking about an empty energy level. Okay. If your energy level is occupied, this number will be what? Just 1. So, only one electron can occupy an energy level, correct. So, this will be a filled energy level. So, you cannot talk about multiple electrons occupying the same energy level, right. So, each energy level is occupied by one single electron. Therefore, you have two possibilities. One, you have an empty energy level where you do not have any electrons, and you have an energy level which is filled by only one electron. Okay. So, therefore, in this case the calculation of z becomes relatively easy. So, you have summation, this summation will run over the empty energy level and the filled energy level. Okay. So, for the empty energy level, so this particular portion will be 0. Okay. So, therefore, in this case the corresponding value of E I will also be 0. So, we can just write this as, therefore, for the empty case minus 0 plus for the filled case you have e power minus E I, this is the value of the filled energy level, okay, which is non-zero, minus mu N I by k B T. So, in this case N I will be equal to 1. So, essentially the value of Z becomes 1 plus e power minus E I minus mu by k B T. So, the way you have to interpret is, if there are no electrons, basically there is no energy for that particular level. Okay. So, the energy possessed by the electron, if there are no electrons, it is 0. Okay. Similarly, if you are talking about a filled energy level, so you have a particular value which is E I for that filled level. So, there are only two possibilities, you have an empty energy level or you have a filled energy level. The empty energy level, there are no electrons, so there is no energy. in that case. Okay. So, if you substitute this, you get the partition function, which is now just two values, either you have a empty one or you have a filled one. So, the summation becomes pretty easy now. So, after this we substitute back into the probability P of E will be e power minus E I minus mu n I by k b t divided by you have 1 plus E minus E I minus mu by k b t. So, the next step would be to therefore calculate the number distribution function.
So, this is just in terms of one electron of a.
Correct. So, this is just you are looking at one particular energy level. So, where only one electron can occupy this, unlike molecules or phonons, for example. Phonons, many phonons can occupy an energy level, whereas in case of electrons, okay, your Pauli's exclusion principle states that depending on the spin, okay, again, so spin will give you a degeneracy, but if you have a plus half or a minus half spin, so this can occupy only one energy level. Okay. So, therefore, it is like saying an electron with a spin of say either plus half or minus half will occupy this. If there is nothing occupied, there is nothing there. Okay. So, you have only two possibilities, either it is occupied or it is empty. Okay. So, depending on that, we only get two terms into the summation.
Sir, according to that wave function phenomenon, that for a same number n value and for a different L and M value, we get the same energy level for energy value for the different electrons.
Right, but so for which concept you are talking about?
Wave function that for
Wave function for
electron for that.
for the electronic energy levels.
Yeah, if you consider that n for two value and L has a two different values 0, 1 or minus 1, and based on that M value plus or minus 1, 0, and we get the same energy level for.
See, but that only the quantum mechanics will tell you, I mean from that state, you know, so how the electrons can actually have these discrete energy levels. But suppose you want to fill these electrons into these spaces, you have only two possibilities, either you put one electron into one space or there is no electron filling one space. So, here what we are doing is we are allotting, we have certain energy levels from the quantum mechanics, but we are now putting the electrons into those, fitting into those energy levels. So, there are what it says now, according to Pauli's principle, one electron has to go and occupy one energy level. Okay. So, there are only two chances. So, one, it can be occupied or it cannot be occupied. So, only for those two discrete states we can do the summation here. Okay. So, therefore,
Should it be some like the denominator has sigma overall, right?
Yeah, but so this is only, we are summing in this case only the filled and empty ones. The summation is only over the filled and empty ones, and the filled one will have a particular value of energy E. So, what we will do is we will complete this exercise and then we will understand how it is going. Okay. So, now we have P of E, the next step is to therefore calculate what is F. Okay. And how will we get F? So, we will be having the number density occupying a particular energy level multiplied by P E of I, correct. So, therefore, based on this, again you can talk about two cases, one in which you have no occupancy 0. So, this will be 0 times P E of I, the other is fully occupied 1 times P E of I. So, therefore, this F now becomes, this is completely 0. So, you have same as what we have written here, E of I minus mu n I by kBt divided by plus e power minus e by kBt. Okay. So, therefore, if you multiply throughout by e power ei minus mu ni by kBt, the numerator and denominator. So, the numerator becomes 1 and denominator will have e power ei minus nu by kBt plus 1. Okay. So, this resulting distribution function is called the Fermi-Dirac distribution function. See, I think your point is correct. I mean, but however, in the case of deriving the Fermi-Dirac distribution, it is, however, I was also checking couple of texts and literature, they do not sum it over the discrete energy levels of all the possible states. So, they only look at either an occupied state or an unoccupied state, and then they only sum it over those two states. Okay. So, this is the characteristic of the Fermi-Dirac distribution function. Okay. So, unlike the case of phonons, now when we do phonons, now you will find that again we will be able to sum it over all the possible states. But in the case of electrons, to derive the Fermi-Dirac, the summation is carried over only through either a empty or a filled state. Okay.
Because it's a grand canonical ensemble.
Correct. So, this is a characteristic of grand canonical ensemble, correct. So, I am not going into all the details. So, I am only giving you the principle of how these distribution functions are derived, okay. But that is true. So, this is basically the principle behind the grand canonical ensemble, correct. So, ultimately now we are arrived at a distribution function for electrons which looks quite different from the Boltzmann distribution function. Now, if you want to plot this, so this is a very important distribution function. So, on the vertical axis I have this number density distribution corresponding to particular energy Ei, and on the denominator I can plot, for example, E of I. So, that means you have these discrete energy levels. For a particular value of Ei, you should know what is the number density that is occupying this energy level Ei. So, that is given by this Fermi-Dirac. So, if you plot this for given temperature, because you see that this is also a function of kBt. So, for a given value of temperature, let us say we will start with 100 Kelvin. So, this will look like this. So, this can be some value 0 and it can go up to say 1. Okay. So, now this is at temperature of 100 Kelvin, and if you look at the distribution, it should be kind of antisymmetric about the value of the chemical potential mu. Now, this chemical potential will be equal to the Fermi level if you are plotting this for 0 Kelvin. So, at 0 Kelvin you would probably get something like this, okay. And at that particular value this will be equal to, mu will be equal to Ef at 0 Kelvin. So, this will be say T equal to 0 Kelvin. Okay. So, that means about the center line here is given by the chemical potential. So, at 0 Kelvin this chemical potential will be equal to the Fermi energy level. So, this distribution will be antisymmetric, and if you continue plotting this for higher and higher temperatures. So, you will see that if you for example go to 300 Kelvin, you will be getting something like this. So, this will be at 300 Kelvin, and it tends to become a straight line from the characteristic distribution like this. At lower temperatures it tends to go to straight line, and finally at when you say 1000 Kelvin it will be just straight line like this. So, this is your typical Fermi Dirac distribution function, and for the case when your E minus mu in the numerator, for the limiting case we can say when your E minus mu is much greater than kBt. So, what happens to this term? Compared to 1, exponential of this term will be very large, and therefore, you can simply write this as e power minus E minus mu by kBt, right. So, what is this? This is your Boltzmann distribution function. So, for the limiting case of E minus mu much greater than kBt, your Fermi Dirac distribution reduces to the Boltzmann distribution function. Right. So, this is the typical nature of, although the Fermi Dirac looks like a unique distribution function, we should also be aware that for large values of these energy E, which are much greater than your kBt, so these can actually collapse into the normal Boltzmann distribution function. Oh, okay. So, therefore, this is an important point. What we will do now is look at the final energy carrier, which is the case of phonon. Okay. So, now on similar lines, so we have to start with the corresponding probability distribution function for phonons and evaluate the partition function z by substituting the phonon energy, that is the vibrational energy that we had derived. Okay. And so, you please start it, try to evaluate what should be z, because there are some mathematical steps involved in that. I will help you with that one. Okay. So, I will also once again give you what is your phonon energy levels, that is h nu times n plus half, where n can be 0, 1, 2 till infinity. So, these are the discrete values of energy levels. So, this is your partition function, right. So, we are now looking at canonical ensemble. So, it will be just e power minus E I by k b t, and just E we have substituted into this. So, now how do we evaluate this particular summation? Okay. So, we can just split this up into e power minus h nu by 2 k b t e power minus n h nu by k b t. So, I am just splitting this into 2 terms, and therefore, you can write this as, you can take out minus h nu by 2 k b t, because this is independent of n, right, and then the summation can be applied to this other term, and we can expand the summation. So, therefore, if you put n equal to 0, this will be 1, okay. And then for n equal to 1, so you have e power minus h nu by k b t, right, plus n equal to 2, you have e power minus h nu by k b t the whole square. So, basically e power minus 2 h nu by k b t can be written as e power minus h nu by k b t the whole square, so on and so forth. So, you have all the other higher order terms till infinity. So, you have now a series expansion. Okay. So, you can compare this to the Maclaurin's series. So, you have 1 minus x inverse can be expanded as 1 plus x square plus x cube and so on. So, you can therefore compare this series expansion to the Maclaurin series, okay, and just hold on there. So, we will not so therefore, we can write z in terms of e power minus h nu by 2 k b t, and from Maclaurin series. So, therefore, so this entire right hand side is equal to this. So, therefore, we can replace this with what, 1 minus, so x will stand for e power minus h nu by k b t. So, e power minus h nu by k b t the whole inverse. So, this is the way we can evaluate this summation. Okay, now you have the partition function. So, therefore, p e of I will be e power minus h nu into n plus half by k b t divided by the partition function. So, therefore, if you knock off the common terms, if you simplify, what do you get? So, minus e power minus h nu by 2 k b t can be cancelled off, numerator and denominator. Therefore, you will have e power minus h nu n h nu by k b t in the numerator, and this term we can take it to the numerator, minus h nu by k b t. Is that clear? So, therefore, we need now the number density function f, which can be therefore written as your ensemble of your n, which is nothing but summation n equal to 0 to infinity. This is your number density at each energy level, corresponding value of probability you have to multiply and sum this over all the discrete energy states from n equal to 0 to infinity. In the case of electron, we did this only for the occupied and the empty state. Now, for the case of photons, we are summing it over, it is a canonical ensemble, we will sum it over all the discrete energy states possible. So, now therefore, if you put it into this, you have again another summation coming up. Okay. So, you have therefore 1 minus e power minus h nu by k b t, and the corresponding value of n, this n I is nothing but, so you have n e power minus n h nu by k b t. So, I think this now involves a little bit so what we will do now is to again use the Maclaurin's theorem. Let me see. So, this should be written as 1 minus e power minus h nu by k b t. We can take it out, again this is independent of n. You have n equal to 0 to infinity in the summation, and the summation is applied to this term right here. So, now we will just use a differentiation rule here. So, if you are talking about minus d by dx of summation n equal to 0 to infinity e power minus n x, let us say, where x can be h nu by k b t. Okay. So, I am just giving a differentiation rule. So, if you differentiate this, you should, what you should get, summation n equal to 0 to infinity, you have n e power minus n x, right. So, therefore, this term here is similar to the right hand side of this rule. So, therefore, we can replace this with minus d by dx of this. Okay. So, therefore, your f now is 1 minus e power minus h nu by k b t into minus d by dx of sum 0 to infinity minus n h nu by k b t. So, now the summation of this 0 to infinity e power minus h nu, again coming back to how we did with this Maclaurin series, this entire summation of these terms 1 minus 1 plus e power minus h nu by k b t plus this square plus this. So, this is nothing but Maclaurin series 1 minus x to the power minus 1. So, therefore, the same thing can be applied again to this term here, summation term. We can apply the Maclaurin series, again reduce it to so 1 minus e power minus h nu by k b t times you have minus d by dx, and you have 1 minus e power minus h nu by k b t, the whole inverse. Is that okay? So, therefore, if you differentiate this, can you complete it, what you will get? So, this x is nothing but h nu by k b t. So, you can rewrite this as x, because I have written this as d by dx. So, it will be easy for you to differentiate in terms of x. So, this also you can write it in terms of x if you want to simplify it. So, therefore, you have 1 minus e power minus x and then you have to differentiate the next term. So, this will be e power minus x by 1 minus e power minus x the whole square. So, this term if you differentiate, that will be e power minus x by 1 by 1 minus e power minus x the whole square. So, therefore, if you cancel the common terms, therefore, you will be having finally 1 by e power x minus 1. Okay. So, this will be 1 minus e power minus x. So, I will multiply and divide by e power x. So, I will be ending up with 1 by e power x minus 1. So, there is nothing but 1 by e power h nu by k b t minus 1. So, a lot of mathematical manipulations are required. So, finally, therefore, we reach this distribution function for phonons. This is called your Bose-Einstein distribution function. So, if you want to plot this distribution function just like the way we plotted the Fermi-Dirac, again this is a function of temperature, right. So, on the y axis you can have the distribution f, the number distribution. On the x axis you can have what? In the case of electron we have energy, in this case we have the frequency. You can write this h nu also in terms of h bar omega, right. This is also h bar omega, multiply and divide by 2 pi and you have modified Planck's constant times the angular frequency. So, you can therefore plot this as function of frequency either nu or omega, it is up to you in terms of hertz for example. And how does it vary with temperature? So, at say 100 Kelvin you will have a function which is like this. So, this is at 100 Kelvin. Say at 300 Kelvin this will be looking like this, and as your temperature keeps increasing, so the number distribution will approach 0 for larger values of frequency. So, this will be for 1000, and if you are looking at 5000 Kelvin, so this is the way that the distribution function behaves when plotted as a function of frequency and temperature. Okay. Once again, similar to the Fermi-Dirac case. So, for the limiting case where you have h nu much greater than k b t. So, this term will be significant over 1. So, therefore, this will simply reduce to e power minus h nu by k b t, which is nothing but again Boltzmann distribution. Okay. So, for these limiting cases, so very high values of energy. So, that could be that you are looking at values of nu which are very large or values of temperature which are very small like this. So, for these cases this distribution function will approach your Boltzmann distribution function. So, we will stop here. Tomorrow we will summarize these distribution functions that we had derived, their most important characteristics. So, now that we have the number distribution corresponding to each energy state, now we can do all these ensembling, ensemble averaging to calculate the macro scale properties. So, we know what is the number density, therefore, if you multiply it with the corresponding energy, you will know the energy of each state, right, and then if you sum them over, you will get the total energy of the system. So, you have basically a distribution function which tells you how many number of energy carriers can occupy a particular state, and now if you multiply it with that energy of that state. So, it will give you the energy weighted average, it is a weighted energy of that particular state, and if you sum them over all the states, this will give you the total energy or the internal energy of that entire system. So, from therefore, a micro state, from the discrete micro state energies, now we can use these distribution functions to calculate the entire macro scale energies. So, we will do these exercise tomorrow. So, we will look at how to derive the internal energy for electrons, phonons, molecules. Okay.